I'm Alistair Funge, Space Policy and Operations Engineer, and I listen to the Cold Star Project.
This show is for entertainment purposes only and is not intended to be what is termed professional advice. The Cold Star Project is proudly presented by the Operational Excellence Society. Cold Star Tech is a supporter of the OPEX Society, and Jason Kanigan is a member of its board of advisors. Talk with us at Cold Star Tech to find out more about the OPEX Society and what we can achieve together in your organization, or just visit opexsociety.org. Thanks for joining us for today's show. Today we're meeting T.S. Kelso. He's a pretty awesome guy. He's a doctor, his PhD, mechanical engineering at operations research. Oh, that's a good thing, operations research. If you don't know what that is, go Google it. It's a thing that I do a little bit of myself. Guess what? From the University of Texas at Austin. All right, Dr. Maury Baja, that's his home turf. I think that Dr. Kelso was there a little bit before Moriba got there. I'll have to check my dates, but it's a neat connection. When you get into the study of satellite identification, tracking, and orbital prediction, you're going to run into him. He is, okay, this is a mouthful, okay, currently a senior research astrodynamicist for something called ComSpock's Center for Space Standards and Innovation, and works from Hawaii. So we had quite a fun time connecting because of the time difference, and Dr. Kelso's a busy guy, and so it took us many months to get to do this. So I really appreciate TS for carving out some time, and we had a lot of fun talking about this. The second direction is TLEs, and anytime you get, these are two-line elements, and this is how satellites communicate information back down from orbit to the ground stations, and then to be entered, this data is to be collected and entered into various software programs to figure out, all right, who's what, where, why, and it's not so easy. And we're going to talk about a lot of things to do with identification and tracking and the evolution of that process in this discussion. And you're going to hear how you put 60 Starlink satellites up there, and yours is maybe mixed in there. How do you know what's what? Which one's yours? They all look the same. They all bounce back the same kind of light. They don't have transponders, right? We know this. So we talk a lot about this, the process of how he got involved. He was the guy who at first in the 80s asked for the data. Hey, NASA, and the tracking groups, can we have this data? And then what do you do with it? You've got to create a program to analyze this stuff. And again, I started off this discussion with the very innocuous question, right? And I don't think this was on our worksheet that we go through to figure these things out. I organized these interviews, and most of the time we cover the Q&As ahead of time, but I just had a sudden thought to ask about, how do you do this? You're going to hear what we get into. It's fascinating. All the things that we're used to today, the standards and the agreements and all that, it's easy to send each other PDFs or GIFs or other kinds of files. Back in the 80s, the early 80s, and I was there. I was a kid, but I was there participating in this to some degree. It wasn't that easy. Your computer didn't talk to that other computer over there. There were different kinds. There wasn't a standardized kind of format to send an image or data by. There was a lot of communication problems. Think about the effect on collaboration and all the advantages that you and I have today. So let's get into it. This is a really fun discussion. I waited a long time for it, and really glad we had it. Dr. Kelso, welcome. Let's talk for a minute about how you got started in this field. You were a young man, and at some point you went to NASA and you asked for the TLE information to be mailed out or something. Tell us a little bit about how you got involved in this, what the spark was, and what made you even think about doing this in the first place?
Well, this will definitely date me, but kind of started in the late 70s. So back then, people didn't know what a personal computer was. And I actually had a TRS-80 Model 1, and I was trying to do some things like predict the positions of the planets. Not that that hadn't been done before, but I wanted to learn how to do it and learn how to program to do it. And one night, we're like 70 miles from Kansas City. I've got this little dinky TV, black and white. And the weather guy says, hey, Skylab is getting ready to come down, but if you go out tomorrow night and look here, you can see it going across the sky. And so I called one of my friends and we went out in the backyard, and sure enough, there's this dot of light just kind of going slowly across the sky. I often wonder what would have happened if it had been a cloudy day instead of a clear day. But I looked at that, and that was the spark. It was, I want to know how to do that. Mm-hmm. And so it was some years, and of course, what your listeners probably aren't aware of, because probably a lot of them weren't born then, is that we didn't have the internet and we didn't have any kind of electronic communications. And so you got information through magazines. And so one day I get a magazine that says, here's this satellite tracking software. And I got a copy of it and then started trying to reverse engineer it. And at the time, this was early 80s, I'm at the Air Force Institute of Technology as a graduate student, and our class leader had worked in Cheyenne Mountain, which is where the Air Force used to do all their satellite tracking out of. And it's like, I can't figure this out. Do you have any idea what this is supposed to be? And he's like, oh, that's SGP4. And of course, my initial reaction, just like many people that come to CelesTrak, was, what the heck is SGP4? And he explains to me it's a propagator and you have to use this data. And I had a sample of the data, and it actually came on like a one-page sheet of paper with what we now call a two-line element set at the top of it. And he's like, oh, you use that and you can predict it. And if you go out on the Defense Technical Information Center, you can get a copy of the report that explains, what's going on. And so I did that. And, over the process of doing that, it's like, well, I need to have data to be able to figure this out. And you couldn't email or go on their website because none of that existed. So it ended up, you wrote them a letter and then you waited, a week or two, and then they'd start sending you pieces of paper in an envelope by first class mail, a couple times a week, and then you'd sit down and type it up. And so that was kind of how I got started. And you can imagine that was a challenge doing it for just a handful of objects you might have wanted to watch back then. And with the thousands and thousands of objects we have today, that would be unmanageable.
Right. Wow. Well, I grew up in the 80s. I was born in the 70s, and we had a Commodore 64 growing up, which is a little bit further along from the TRS-80, but not that far. And I remember getting Compute magazine, and they would have games in there that you would have to type in BASIC, or they had a machine language thing, and you had to have an assembler in that, and it would check for you. And you would never know, is this good enough until you typed it all in and then you did a checksum, right? So I remember that. I grew up with that. So, and I'm still thinking even now, like you mentioned the TRS-80, and I thought, what? Can that thing handle this sort of, like, what complexity of equations could a TRS-80 handle?
It probably really didn't get to the part where I was doing that on the TRS-80. The real challenge up front was, so I would get this stuff in the mail, and I would, I'd come home and I'd type it up, and then I would go out and look to see if I could see a pass. And so after I finished at the Air Force Institute of Technology, I went to the Sunnyvale Air Force Station, which is what it was called then, eventually became Onizuka Air Force Station, and now I think it's closed, but where we did satellite operations for the Air Force. And it was in Silicon Valley. It was when, a lot of the communication stuff was starting up, and we had these groups of people that were doing software for what we called an electronic bulletin board. So the concept at the time, there wasn't there was internet, but we didn't have access to it. And so the only way you could do it was, you had a modem, which, some of you may have heard historical beeps and chimes or whatever from what a modem sounds like. But you would hook that up to your phone, then you hook the computer up, and then somebody else would do that, and you do it usually at a blazingly fast speed of 300 bits per second. So really, really, really slow communications. But we started setting these up and playing around with the software. And one day I got this idea. It's like, I come home every day and I type this stuff up, and I bet there's other people out there that would want to do the same thing. And so if I type it up and put it on the bulletin board, then they could just come in and get it, and they wouldn't have to retype it, as if there were actually other geeks out there that one wanted to do it, and two could actually find your phone number to be able to call up your computer. But somehow that did manage to work. And so that was kind of the challenge, right? I mean, you're going through this, how do I do the connection? And so the TRS-80 ended up being more of the, how do we establish the communications and eventually do things, because even concepts like there wasn't such a thing as a PDF. So when you wanted to put out a document, what format were you going to put it out? We didn't have GIFs, didn't have JPEGs, none of that. And so all of that was a learning experience in trying to figure out, how do I convey information to people so that they can do this? And really the motivation was to do all the parts of what's the software you're supposed to use and how do you get it easily, and then what's the data you're supposed to use and how do you get that easily, and then allow people to go off and innovate and do their own thing on top of that without having to constantly reinvent that process.
Yeah, that's super exciting. And I'm glad you brought up the lack of GIFs and PDFs and things like that. I think people today take collaboration very lightly, like, oh, it's so easy now with Google Drive and sharing files. And I can remember where there were multiple word processing programs that were fighting it out, right, for supremacy in the marketplace. And you'd be like, well, word perfect. All right, now I got to turn this into something else, right? And nowadays we've got APIs, and they'll talk to other apps and give access and make it all work, right? It's so much easier. So you were figuring this stuff out at the time. How often, I guess, was it challenging in the sense that, like, so you'd give somebody the data and they'd get the program to run it through somewhere else, and then they'd go off by themselves and create something else with it? Was it easy or difficult when they'd come back from their journey sort of with something new to disseminate that, or to get other people to be able to use it?
It was really a challenge. When you think about how do you exchange information? One of the first things you need is a standard. And so, we have eventually developed things like GIFs and JPEGs. But one of the kind of offshoot things that I ended up working with early in this process, and this was probably like the mid 80s when I went to the University of Texas at Austin to get my PhD, was I got involved with these guys that they were pulling down satellite imagery off of the NOAA polar orbiting weather satellites. And so they needed to know how to predict where they were going to be and where to get the data and that kind of stuff. And we got into this exchange, and it's like, wow, this is really cool. I want to do this. And so I got, an antenna and a receiver, and, figured out how to hook it up. And that in itself was a challenge. And you think, well, okay, we're done. But there was no real graphics standard. So, you had to figure out for every individual machine, there was a unique way to get the graphics to display. And then if you wanted to say, hey, I got this really cool weather image over Texas, and send that to somebody, say, in New York, there wasn't any way to do it. I mean, it was on your computer, and there was some custom, proprietary data file that you can load into a specific type of software that only worked on your machine.
Computer. Right.
And so, that was like right before GIFs came out. And then it's like, hey, if we can figure out how to encode it as a GIF, then we can share it as if anybody had GIF viewers at the time. So yeah, initially it was a very, very difficult process just to be able to exchange the information that you needed to do it. But we eventually got to that point, and then JPEGs came out, and I mean, there were all sorts of things that other people, for other purposes than doing satellite work, we're starting to understand, like, yeah, we need this. We need some way to interchange images, for example.
Mhm.
And so it was a good time. I often wonder how I had the time to do that while I was
Right.
working on a
Right.
PhD, but I'm lucky that I was.
Wow. Well, folks, take a moment and just consider how difficult collaboration would be, how much slower the process of iteration and learning would be if we had to figure out how to communicate every time somebody new came along, to get it to talk on your computer versus theirs. It must have been extremely challenging. I wasn't even doing anything like that as a kid, right? I was just putting games into my disk drive and running them, or typing a few things up. But man, that's complex. So you've seen this for a long time. What I'd like to do, you mentioned standards, and I want to get into standards and how important they are, and how this should be evolving. What's the truth about the current state of U.S. technology when it comes to satellite identification and tracking?
Let's just say there's a lot of challenges there. I mean, one of the things that I don't think a lot of people really appreciate, you don't want to focus on the past
Mhm.
and, trying to do things the way they've always been done. But to some extent, we all face issues with what I'll call legacy hardware and software.
Mhm.
So it's like, this system was developed at a certain point in time, and then for whatever reason, it's not updating. And one of the classic cases of that we see in satellite tracking is what has been developed as, what's called the U.S. Space Surveillance Network, or SSN.
Mhm.
So there's sensors and there's computation centers. The 18th Space Control Squadron operates that, for the U.S. government today, and so they collect observations and they process it, but they're doing it based on development work that was primarily done in the 70s. So things like SGP4 and the format that we use for the GP data, the general perturbation data, or TLEs, was developed in the 70s. They had such limited bandwidth that they were trying to cram as much information into two lines, and at the time it was actually two cards, with the kinds of stuff that we put
Cards.
in a hopper to feed into the computer. And so they were trying to fit that in there, and they used a 2-digit year. We often rue the day that somebody decided to use a 2-digit year, because that causes all
Mhm.
sorts of problems even today. And but they actually considered a 1-digit year, because it was such a premium on things like bandwidth. So we're still using a format that's tied to limitations of computer systems back in the 1970s. And a lot of the software that was developed back then didn't, I mean, they assumed, I'm sure, that those systems would be updated eventually. And unfortunately, they have not. I mean, this
Mhm.
is, this is kind of a broader issue, but the US government and the Department of Defense in particular has failed on multiple occasions to try to update that. And so, we were stuck with this system that was not designed to do it. So when you see things that might be limitations there, so tracking or identification, it's not so much a failure of the people or the system. It's a failure of the ability to update it, because when these systems were developed, nobody had a concept that we would be doing things like launching 60 to 100 satellites at a time on a booster, or that we would have tens of thousands of objects that we were tracking in Earth orbit. I mean, they just weren't projecting the environment in that way. And then, of course, the things like, one of the things that I work a lot with is on the safety of flight side. And we constantly get in this issue of, well, how do you predict close approaches for satellites? And people will say, well, TLEs aren't good enough for that. Well, they weren't designed to be good enough for that. It was never envisioned when that was designed, that you would have these close approaches happening thousands of times a day, and you would need much more accurate data. So So the first limitation we have are these legacy hardware and software issues. And so now we're in the mode of, well, how do you overcome some of those? And so some of it is done through standards, and standards are important. And so one of my jobs, I have kind of a weird job description, I guess, but I'm part of ComSpot. We have a center called the Center for Space Standards and Innovation. And of course, standards is an important part of what we do, because if you want to go off and innovate, you'd rather not have to reinvent the wheel every time you start to do that. So you need to know, what format is the data going to be in, what software should I use, what's the accepted version of that software, all of those kinds of things before you go off and say, okay, now I'm going to stick my neck out and predict whether these two satellites are going to collide or not. And so it's a non-trivial issue, but if you don't do that up front, then you're going to run into issues later on with what you're trying to do. So now we're in an environment where technology is advancing, and I don't know that they necessarily just discount the limitations of the system. I think a lot of people assume that the US government, with all its resources, must be able to do all sorts of magical things with tracking anything in Earth orbit. And while that may be the perception, the reality is a little bit different, and it's because of those legacy limitations. So when we launch, let's say, one of these launches where we've had 100 CubeSats on it, and if they're all pretty much the same size and shape, and you just dump them off of a rocket body, an upper stage, and now the radar picks it up, well, one, it wasn't really anticipating when it was designed to do that unless it was a missile attack. so the response is going to be a little bit different than you would for satellites, and all of those objects are going to look exactly the same to the radar.
Right.
I mean, so it doesn't know. It's like, well, I see one 3U CubeSat here, and I see 50 other ones over here. I don't know which one is which. And you think, well, that's okay. You see them, right? But if you think about it, the challenge is we want to know where they are going to be, and so you have to be able to predict them. Well, to predict them, in orbital mechanics, it's reasonably straightforward. Now we have complications from atmospheric drag, but it's reasonably straightforward to say, oh, if I know where the object was in the past and it's acting primarily under the influence of gravity, I can predict with good confidence where it's going to be in the future. And the problem is, to connect the dots, if you will, you have to know which dot goes with which object. And so when you see 50 of them and they all look the same, and now you're trying to connect the dots and they go over one sensor and you see 50 dots, and they go over the next sensor, maybe you see only 48 dots because of observing geometry or whatever, and you're trying to connect all those dots to get orbits, it's difficult to do. And if you don't do it right, then your prediction doesn't work, and your correlation between new observations and that track, start to break down, and now you have to revise the track, and it may involve revising, some of the past associations. And so it's a time-consuming process just to get the orbit. And of course, when you have these objects that are in close proximity, trying to do the association between, well, that object, is this orbit, but I don't know what that object is, then it's like a whole other level of complexity. And the challenge there becomes kind of a mission assurance problem. It becomes, if I say a university builds a CubeSat, and we're going to do some kind of research, and we plan everything out, we know how it's going to be launched, when it's going to be launched, and what the orbit plane is, and lighting and all that. And then we make the assumption that, oh, but by the time it comes off of that rocket body, I'm going to know exactly where it is and which one is mine. That's not going to work. And so if you have to do something like, oh, I have to bring these systems online and do something with the solar panels before I can, really get this thing working. and you assumed you were going to do that the first day, and it takes 2 weeks to identify your satellite could be dead. And so we're trying to get people to realize it's like there's limitations here. Now we at CelesTrak, one of the things we do is we work, and we do this on everything, right? We really, after that experience I described earlier, appreciate the value of collaboration. We as a community can work together to resolve a lot of these limitations until these other systems and some of the newer commercial systems start to come online to support it. But we work with SpaceX, for example. They've launched over 1,300 satellites now, and so you think about it, they launch them 60 at a time, and we have the same challenge. They all look the same, the radar. SpaceX though knows which one is which because they're communicating with everyone. They're able to get GPS tracking off of it and build their own orbits, and then they can generate a prediction that says, oh, here's where my satellite's going to be. And so we work with them to do something that we call supplemental TLEs or SUP TLEs. And it's, instead of it being TLEs derived from observations from the Space Surveillance Network, it's TLEs derived from the ephemeris that includes predicted maneuvers for like the upcoming days, so that we don't get into that, well, which object is which, how do we do all these, so we can cut through all of that without a single sensor. But it takes collaboration, it takes a little bit of innovation to try to look at the problem and not focus on the problem. Don't focus on the obstacle, but focus on what are the ways to get around that obstacle so that we can do what we need to do.
Okay. Well, you covered a lot in there,
No,
including there's several questions here that you answered. So one of the questions I have was, what should we update first, technology or standards? And I think standards is your answer. And then the importance of collaboration with operators. If the operators will collaborate with you, then you're able to speedily get through the problem of what's what and get to the business of the orbital pathing and predictions. So that's really, I think, an important thing. And this is good because this is so far, from my perspective, been a slightly different conversation from what I might have had with Dr. Morabajah, for example, right? Where we've covered some of the similar concepts, but I think, it's great because you're coming at it from a different angle here.
right.
So other than this huge, massive satellites suddenly that are getting thrown up there, what other concerns do you have about the future? And I guess here's a question that's popped out while you've been explaining. Why has the United States government, in your opinion, shied away from updating the technology?
They haven't really shied away. They've actually had, and I've literally lost track of how many times they've done it, but there's been probably 4 major programs. I mean, multi-billion-dollar efforts to update, the systems. And it, every time it has failed, I'm sure the reasons why they have failed is, far too complex to get into, even if I did understand them. But the fact is, it's not that they haven't tried.
Yeah.
It's that they haven't been successful. And so, you have to consider that, and you can frame this any way you want, but space is a global community. And so, we all have to figure out how to collaborate. But even if you look at it from a narrower perspective of the United States government, it's certainly a national security type of issue. And so, you get into things like, well, okay, the Department of Defense obviously has its own mission in the interest of national security. But if you don't know what the background is that's going on, all this commercial activity today, it's kind of hard to focus your attention on where you think there might be national security threats. And so they need to update this, if for no other reason than the national security stuff. I think we as a larger community are starting to realize that we really shouldn't depend on, and I'll just say, national security interests to get the data we need to do science and commercial activities, because there's a conflict of interest there, right? So I mean, one, we know, as we just discussed, there's limitations, with some of the legacy systems, but probably more importantly, and we all know this is true. I mean, we're not revealing anything secret. The fact is, when you get to national security issues, the people that are dealing with those tend to be less than transparent. And that is really not in our best interest when we're trying to do things like avoid collisions in orbit.
Mm-hmm.
So you really need to know not so much what something is doing, but where it is. You need to know what the confidence in that solution is. You need to be able to share it using, standard interchange formats, those kinds of things. And the more we make it proprietary, or there's issues like national security issues that say, well, I really can't tell you where this object's going to be, as if nobody else could figure out where it is. And
yeah,
right.
yeah.
And so there's a lot of that we have to break through. And so, on CelesTrak, we're trying to enable people to go out and do that. I don't want to enable people to do bad things with it, but we know any technology can be misused no matter what you do.
Mm-hmm.
But the objective is to share the information, to be as transparent as possible, to try to provide the foundation, if you will, where we're doing all the checks. We're trying to make sure that the data is reliable, that it's easy to find, and we're dealing with a lot of data now. It's easy to find when things go bump in the night, and then to make sure that whoever is generating, say, the primary source of the data, whether it's 18th or it's coming through SpaceTrak or it's some other organization that we get data from, that we immediately advise them of the problem, so that when we can help them get it worked out, show them what we're seeing, and then we fix the problem once, and then all the literally millions of people that use CelesTrak aren't faced with the challenge of, oh my God, now this isn't working, and they've got to all go off and try to debug everything, right? That would be a tremendous waste of resources when they're really trying to do something else other than be a software engineer.
Right. Yeah, and I've talked about this issue with Ralph Dinsley of Norse, who had ran Fylingdales. Folks remember that the Britain missile defense system is actually run, or the data comes from the United States installations, and then Fylingdales is the operations center for that in England. But he was very adamant, coming from that national security armed forces background, that this stuff needs to be moved out from behind the national security firewall, and that collaboration is going to help everyone. So we've got a standards issue. I have heard that TLEs truncate data, that there actually is more data transmitted in many cases. Is this true, that the data is cut off?
Well, there's limitations, and so you'd asked the question about standards before. What should come first? I didn't really answer that question, but if you read between the lines, you realize, like, oh, the technology usually comes first, and then we're scrambling to try to put standards in place to deal with it. So we have a lot of people innovating, and unfortunately, in a lot of cases, they decide, I'm just going to go off and do this, and then everybody will catch up. And usually, once you get behind, that's a hard thing to do. But so the TLE data is, and I briefly mentioned, it's really what we call GP data. So there's different models for propagating orbits, and any model has simplifications, and so there's an issue of fidelity and the kinds of performance you're trying to get. But because of the lack of bandwidth and then compute power, the U.S. government came up with SGP4, Simplified General Perturbations version 4, that is focused on being able to be as computationally efficient to meet their requirements as possible. So we use that. We have a format, but because they were trying to put the data into the format, so we talk about TLE data, it's really GP data in a TLE format. But when they put it in the TLE format, they did things like, oh, we're going to use a 2-digit year because certainly in another 20, 30 years from now, we'll have figured out how to change the format and won't have to limit ourselves to that. And they so used 2-digit year, day of the year. They assumed that we would never need more than 100,000 objects because it's a fixed field format, and they use 5 digits for the catalog number. And of course, we're 21 years now into the 21st century, and we're still using 2-digit years.
Right.
So
yeah. 1951 or whatever is coming up close.
Right. So we
overlap.
just assumed, and we went through this, back in 2000, right?
Yeah.
It's like, oh, it's, the computers will magically know that when you get to 0, that it doesn't mean 1900, it means 2000. They're like, no,
Right.
that's not how computers actually work.
With
And
the numbering problem, is it possible to put a letter in there and start getting far more combinations, permutations?
That's what you get into here, right? And so some parts of the DoD have proposed doing that, and they're actually doing that.
Okay.
But when you think about it, it's just like the Y2K problem. Assuming that when it gets to 0, it's automatically going to assume 2000. It's like, no, that doesn't work. You have to update the software.
Right.
And so the same thing happens here. People say, oh, well, it's just a label. And it's like, no, I'm pretty sure if you actually went into the code that's using it, most of them are assuming it's an integer. So when you do something like you try to convert the integer or add or subtract, whatever that, you don't know what they're doing with that data.
Right.
And so any software that assumed it was an integer, as soon as you say, oh, I'm going to use a letter for the first character too.
A2, fail.
Right.
Right.
Yep, exactly.
Okay. All right.
So
it would work for the satellite
truncation.
numbering, but it wouldn't work for the dates. Yeah. Huh.
Well, it wouldn't work for the dates. And we, you sit there and think, well, we're almost there. And even the numbering, I don't
what do you do
think
with
people
it down
really
the chain?
appreciate. Well, I don't think they really appreciate the limitation, because you say, oh, well, it's 5 digits, 100,000. Current catalog is just under 48,000. It's taken us 60 years to get there.
No.
No, the real limitation is 70,000. Because there's a block from 70 to 100,000 that the 18th Space Control Squadron uses for, let's say, working space. They're doing analysis to try to figure out new orbits, or they're tracking things that they don't know what they are. So we're getting perilously close to that edge, and then things are going to break. And we're trying to avoid breaking it. I think you have, so I'll wait for your questions. I think you have some questions.
Well, I said earlier when you said that there have been multiple attempts to do something about this, and they've all failed. Because if you don't understand why they failed, what chance do the rest of us have in really understanding what's going? I mean, is it just going to have to completely fail, and then finally people are going to say, "All right, we must commit to evolving and solving this problem"?
Yeah, I mean, people tend to be really creative at finding workarounds, right? But yeah, that just provides an opportunity at some totally unanticipated moment that just happens to be a critical moment, what we might call a perfect storm, where that fails and it's going to bite you. And so, we're trying to avoid doing that. And it tends to be pretty difficult to get people to understand that it's easier to do something about it now than it would be later. And actually, the Y2K issue comes to mind, because I remember in the late 90s proposing that we update the TLE format. And the notion was, I don't understand, or you don't understand, it's far more complicated than you're suggesting. And it's like, no, you don't understand, because it's going to be easier to do that with, at the time we had, probably fewer than 10,000 objects in orbit. And now we got double that. And we have literally probably millions more people using that data than we did if they had fixed it then. And so now we're in a situation where it's like, well, okay, we're going to hobble along. You'd think, hey, we got 30 more years before we get to 2050. Certainly it'll be fixed by then. But do you think the guys that came up with the 2-digit stuff back in the 70s thought it would be 50 years and we'd still be using it? I don't think so.
Yeah. Well, going back to the old computers again, I know memory was in short supply, RAM at that time, and they had to come up with very
Right.
clever ways to get programs to operate, shuffle things, use it like virtual memory. But it eventually came to a point where the programs got so big that they just couldn't fit in that format anymore, and they had to upgrade to something else. Plus, there were commercial
Right.
things going on. But that wasn't a national security problem, but it did evolve. So, well, let's talk a little bit about standards, and then I want to cover CelesTrak. CelesTrak's pretty darn exciting. So let's talk about the problem of overcoming like user adoption in standards. So, like, say you've got the Russians running their own tracking. What happens when their prediction does not? When they say this is going to be at this spot at this time, and that doesn't agree with, say, what the French or the Americans have come up with, how often does that happen, and then what happens?
Well, so there's a couple of interesting questions
Yeah.
wrapped into that. I'll see how I
Okay.
can best answer it.
Sure.
So one of the other things that I do as part of my work is I run something called the Space Data Center.
Mhm.
And we're supporting 30 plus operators in the Space Data Association to screen something like 800 satellites every day. And so, and we can only use data that's available.
Mhm.
And so for the most part, we've broken through the barrier that I face. So this kind of started out as Socrates, which is still a program running on CelesTrak, where we daily with the TLE
Mhm.
data predict, where things are going to get close, that kind of stuff. Just to give people a sense for the magnitude of the problem. And then, it's been used in some interesting cases that to kind of confirm something that happened, after the fact. But we're in a situation where it's like, well, we had TLE data, and then the next thought was, well, satellites that maneuver all the time are actually the hardest to
Mhm.
track, from a passive perspective, like the Space Surveillance Network does, because you don't know when they're going to maneuver.
Mhm.
And the concept, when I set up Socrates was, if I can just get the operators to tell me, because they know when it's going to maneuver and they
Right.
know how much it's going to maneuver. And then we will use that data to try to predict things. And what we find, so you're worried about French data and Russian data and all that. Even when we use, and so now we get the GP data, the
Mhm.
TLEs, we get the SP data, the special perturbations, which is a different, propagator, can be more accurate because it incorporates more forces. We get that data now from 18 Space Control Squadron, and we have the operators' data. And when you put those in, oftentimes they don't agree.
Hmm.
So it's not even a question of, well, what would happen if we had French data, or what would happen if we got data from Leo Labs, for example,
Mhm.
one of the commercial
Yep.
operators. But we find that all of these solutions have differences, and sometimes the differences might be pretty small, and other times you're sitting there going, wait, we're all using the same data, why are we coming up with a different answer? And sometimes it's because, oh, well, we're using the latest data and they're using the previous data. And so the question becomes exceedingly complex. And then the layer that you're talking about with French data and Russian data is it's not available. We may have limitations on the US data, but to their credit, they have stepped out way farther than anybody else has. And so, it's really kind of hard to say, well, it doesn't stop people from saying it. It's really hard to credibly say that data is better than your data when you won't share it and you
Sure.
won't allow people to do analysis and everything. And that's where the transparency comes into. And what we see is that if we don't compare the different types of data and do analysis on a regular basis, like a daily basis at least, and find where things don't line up and pull the thread
Mhm.
to ask why, there's a whole host of things that can go wrong. It's a system designed by human beings. They all fail. And so there's a whole host of things that can happen. And the more you're doing, the easier it is for it to get lost in the noise, right? And so there may be something that's going on with 100 satellites out of 20,000, and you don't see it because of that, overall level of activity. And so you have to do this constant, comparisons, and then work with, people have to be willing to collaborate and share and be open to exchanging that information. And we have a great relationship with SpaceTrak, with 18th. And when we find a problem, it's like, hey, we're seeing this. Maybe it looks like you missed a maneuver here, or we have some other kind of issue. And we do the same thing with the operator. If we think that their data is showing a bias because of something that they're doing in their orbit, we'll make sure that we provide them all of the analysis that we have, with the hope that they'll fix it, because ultimately that improves the situational awareness for everybody. So that's a challenge, and I certainly encourage these other activities, Europeans or the French, the Germans individually, Russia, China, anybody that wants to participate, we need to find a way to participate. Now, to address the issue of standards, one of the things that we've done quite extensively, I guess, on CelesTrak is we realize that it can be difficult to exchange data when everybody's using their own format. So they use different, just formats, like how do I get the stuff into the computer? But they use different units, and they use different propagators. And so when you get to that level of complexity, it's like, wow, I have your data, but I'm not really sure I understand how to interpret and predict with your data. That's a challenge. And we do that in the space data. I said there were like 30 operators that we support in the space data center. There's probably at least 30 different formats, because some of them have more than one.
Okay.
So we get into the mode of, we know how to interpret it, and we're going to do that comparative analysis to make sure that our interpretation of the data matches what the operator thinks it should be. And then we're going to translate it into standard products. So we use a common coordinate frame, we use common formats. We do for a lot of those operators, we send their data to 18th for 18th to do screening. But we do that by taking the format that the operator uploaded, doing our magic on it, and then converting it to the format that 18th expects, so that they can do their magic on it. And so those standards, knowing how to get in and out of them is important. And often it's hard for individual operators to do that. I mean, we have lots of experience with doing it, so we're very confident that we're doing it correctly. But it's easy to misinterpret, something simple. And we've found cases where we get the data and then the operator starts asking questions like, well, we thought it was supposed to be this. And it's like, no, it has to be a specific reference frame. And we help them get it corrected, and we move on. But so standards are important, but I really can't emphasize enough the need to be transparent and sharing. And because if you're not sharing and you're not comparing to these other systems, like if you want to look at it from a commercial perspective and a marketing perspective, you can't really honestly say, oh, my data is better than yours, unless you can actually do a comparative analysis. And that potentially is one of the issues that people are sensitive to, right? They don't want to have their stuff look bad, but you can't find when you have problems either. And really what we would like to focus the community on is, let's all work together, find the problems, and help everybody get rid of them. And then you can compete on what you really think your advantage is. I have a better sensor, and I can track more accurately, and I can do whatever, instead of, well, I'm not going to tell you what's going on. You're going to believe, I'm going to hope that you believe my data is better and pay me for it, or whatever it happens to be. Because that's not really the way we're going to work together to protect the space environment.
Right. Well, Some great takeaways from that. The usual of things on the ground are rarely the way that they look up in the air. When you're actually doing the project, you stumble into these issues, right, of formatting problems and that, and units being different that you might not even consider way up on the strategic level of how are we actually going to implement this. The statistician in me is wondering, maybe if all these organizations didn't want to share all their data, maybe sampling, pulling the same satellites. I don't know what would be statistically relevant, maybe 100 a day or something like that, of this particular batch. And we check the same satellites, right, and compare that data. And then you're not having to reveal everything. I know from the data science side of our business, getting a client to fork over all their data, that trust factor is a pretty difficult thing, like especially in the healthcare field where you've got HIPAA and these requirements and that, which is not quite national defense, but it's a similar kind of situation where you're like, I don't want this data roaming freely through the countryside. There is a difference in that you can just stick a telescope up and see something, whereas with healthcare, you can't quite do that. But I do want to echo that I've seen this sort of, no, we don't really want to do that. We'd love to work with you, but sort of situation. Well, that's cool. Well, let's talk about CelesTrak then and finish up with that. I love the application. I remember the first time I found it, I was Googling around. I was doing research on TLEs, what they were. I think I'd like just been told about them, right? So I do the usual thing, right? Go and look for 5 different sources that look trustworthy and compare them and learn, right? And so there's a bunch of definitions, kind of a glossary and that sort of thing. And then from there, I'm like, launch orbital visualization. What does this do, right? And then you see mirror, everything going around, and that was my description, folks who were listening and can't see us. All the orbital circulations, right? That CelesTrak shows you. I'll link to it in the description. I highly recommend you go look at this. It's astounding. And then I moved my mouse wheel and panned out to geo and saw that there were, in fact, more. And there is a lot going on. It's anytime I want to impress somebody with anything in space, really, any concept, I show them CelesTrak, and it has the desired effect. For that. So, at what point? Let's start with this. Did you realize it was possible to build CelesTrak? Obviously, you mentioned Socrates as a starting point, so you kind of had the math going, but then to get to this stage of visualization where now, even 6 months ago, I don't remember being able to see this, but the string of Starlink satellites going by or something like that, right? It looks different now even than it did. So how did it start out?
Well, so we talked about the early stages of CelesTrak, and for many years it was, well, we're going to give you the data, and we're going to make sure that we quality check it, and you know where to get it, and we're going to put it. Initially we didn't have the web, but in 1998, or actually 1994, I guess, we started doing stuff on the web. Right after the web came out. Yeah. And the idea was, we're going to put it in a place where it's really easy to get. So as a text file, you can always go to the same text file, and you're going to get the latest data. Really simple stuff. But it was, as we went through the years, it became progressively more clear that as more people came into it, they were going to do the same thing you just described. It's like, I want to figure out where my satellite is, or some satellite, right? Mm-hmm. And it's like, well, how do I do that? And then you find out, it's like, oh, I have to get a TLE. And it's like, what's that? And you look at the data, and like, what the heck? Right. And so it's like, and so I, kept thinking about it. It's like, well, you've got people that, so it was kind of like an assembly process, like an IKEA thing. It's like, well, here's all the pieces, and here's the instructions, figure out how to put it together and do what you want to do. And over the years, as I've worked with not only people doing satellite tracking, whether it's amateurs just wanting to go out and see something, or, we support a lot of satellite operations centers around the world too. So you got this whole range, but you realize it's like, usually they just want to answer a question. And so the question shouldn't be what the heck is a TLE and what do I propagate it with and which software has that? And then how do I learn to install and operate that software and everything? It's like, yeah, this is way too complicated. So, was looking for a solution. And of course, the company I used to work for, Analytical Graphics, AGI, had developed a technology called cesium. And now cesium is, a separate company, but they provide their framework to the community as an open source package. And so the concept was, I really need to find a way to take all that. We have the data. Now, how do we put it into cesium so that we can visualize it? And you might think, what, how hard can that be? We do that with all sorts of, models. And it turns out cesium is an exceedingly powerful program, but it's not really focused on the space stuff. And there aren't let's say the links into it to be able to do this. And so one of the guys that I met, we're both Air Force Academy graduates, and met him when we were dealing with the Iridium Cosmos collision and the aftermath of that. He ended up going off on his own and developing, this is TJ Coury, went off and developed a technology that takes all of the stuff we're doing with SGP4, so that propagator, and making sure we had the right version of it and that it matches what we see used, say like an 18th Space Control Squadron, and then coded that all up in JavaScript and in a way and made improvements to cesium so that it ran much, much faster for what we need to do in the orbital environment, to the point where, if you go to the CelesTrak homepage and you click on the orbit visualization, in a matter of seconds, it's going to load, an enhanced version of cesium, and then all 21,000 objects that are currently in the public catalog. I mean, in seconds. And so the objective was to go from, there's this really cool software package and it runs on Windows. It's like, oh, dang, I'm on a Mac. And it's like, no, we don't care. It's like it runs in the browser. And so it doesn't make any difference what operating system you're in. If you're using a modern browser, it supports cesium. And so all of the calculations, because if you think about it, so we get roughly 400,000 unique users on CelesTrak a day. And so you could take it from the perspective of, well, maybe we would just run this on CelesTrak. And it's like, wow, that would take like a huge server if you had even thousands of people come in and do that. And so with JavaScript, the beauty is you download that and you run it in your own browser. So it's a distributed computing, if you will. So he designed this tool so that the cesium and the special stuff that he does, I'll say magic because it still looks like magic to me, that he's able to do things like propagate 20,000 objects at 30 frames a second. So do the math on that. That's a lot of calculations every second to update that. And then that takes it away from, well, I have to know what the data is, and I have to know what the standard format is. I need to know how to interpret it. I need to know what orbit model to propagate it with, what software is it on my operating system. It'll run in your browser on Windows or Mac OS or Linux. It'll run on Android, iOS. It doesn't require installation. It just works. And so that's really the beauty of it. And then it allows you to do things to get the people that really need to understand it. So we're talking about standards and technology, and the other aspect we get into when we talk about those is the legal and policy side of things, right? And they're not scientists and they're not computer engineers, so they're not going to go off and probably try to figure out what a TLE is and do that whole journey. And so it's like, I'll give your listeners an opportunity to go out and see how easy this is. Click on the orbit visualization, give it a couple seconds to load. And then at the bottom left, there's a little satellite icon and it'll open a table. And that's a table that shows all the objects, it has metadata about each object. And so you can click any of those. So you click on the catalog number, I think we call it the ID or something like that. But if you click on that, it'll select it and show you where it is on the globe. But you can do things like in the little search box, you can say, well, how many active satellites are there? And just type active into the box and you'll see, wow, there's over 4,000 active satellites. Now, just a few years ago, that was like a quarter of that. And a large part of that is because of Starlink. And you could do something like, well, just show me where all the Starlink satellites are and type Starlink. And then boom, in a second or so, you're going to see all just that displayed on the screen. And so you can say, wow, 4,000, that's a lot of satellites. But so those are all green, the active ones in the display. And it's like, well, what are these orange and red ones? It's like, well, orange are dead satellites. And you might think, well, looks like there's a lot of those, but is it really a lot? And they type dead in that box and you find out, oh yeah, there's like 2,800 dead satellites still floating around in all orbital regimes, right? Is that a problem? And so if you're trying to get a policy person or a legislative person to understand the magnitude in a matter of a minute, like if I were to show you, and we would have too much screen lag with doing it over Zoom, but if you go in and play with it, you can see that in a minute you could run through and say, well, let me type active, let me type dead, let me type rocket body. See, there's like 2,000 rocket bodies that are still up in Earth orbit, and help somebody very quickly understand the magnitude of the problem, where these things are, and then hopefully spark their curiosity to want to go out and learn more about not so much how do I do all that calculation, but how do I go off and now address the problem? How do I convince other people that this is a problem and do it in a way that people that aren't scientists or engineers can readily understand? So that's been the focus, has been how do I take CelesTrak from being a kind of a data repository to take it to being a tool that can easily help people answer questions that they might have today about what's going on in Earth orbit. And you can easily, as you mentioned, see all these like trains of satellites, the green satellites, and those are many of the recent Starlink launches. They're absolutely easy to pick out just on initial inspection, and you move the globe around. It's like, wow, they're everywhere, and and SpaceX is just getting started.
Right. Yeah, it's a lot of fun to use. Data visualization is so important. We have a data science department here. Our chief data scientist, his day job is at a major fraud identification business. That's where I started learning about fraud prevention and data visualization, because once you see it, you can't unsee it. You start recognizing the pattern, and so I know how valuable this is, as you say, to just show somebody, not in the form of a table or numbers, but here's a picture and it's in motion, and it's undeniable. Once you see it, again, you can't unsee it. It's very impressive. Let's finish up with this then, Dr. Kelso. What capabilities do you envision CelesTrak having eventually in 5 years or 10 years?
We're trying to, I guess, push that limit of what we've already done. So the version of orbit visualization that we have on CelesTrak is, I guess it's version 1, right? And so TJ and I have been working on version 2, and it has some really nice enhanced capabilities. And the idea is to be able to take it a little bit beyond that, to the point where, well, you can do this kind of like somebody gave me a view and I'm just going to accept what that view is, to being something that you can customize with like very little JavaScript, right? So you'd write JavaScript on top of it to do kind of high level operations to show how your satellites interconnect, or what things they can see on the ground, or a whole variety of things, and particularly to help with things like conjunctions. When we have close approaches of satellites, to be able to show, a lot of people think of a conjunction as being kind of a one-off, something goes whizzing by something else, but we see what we call conjunction storms, where we have so the two orbits, like if you think of two circular orbits that are intersecting, they intersect on opposite sides of the orbit. And normally you might only see it happen where they are in phase on one of those two intersections. But it turns out that some orbits, and we see this quite frequently, they're intersecting not only every time they go past that intersection, but the one on the other side too. And so you see, like for low Earth orbit, you might see close approaches every 40, 45, 50 minutes or so. And you realize like, oh, well, it's just like playing the lottery. The more times you play it, the more opportunity you have to win, or in this case, to lose. And so we're trying to take that concept and again enable innovation. We've built the framework to allow people to go off and innovate and help educate the community. But that's really CelesTrak's mission has been to facilitate collaboration. So we did that all the way back from electronic bulletin boards to today, and to facilitate easy sharing of the data through standardization, and to promote the use of new standards, and now to make it so that you can innovate on top of that in a much easier way, so that because there's no way, if I live to be a million, that I could do all the things that many of your listeners are thinking about wanting to do right now. And the best way I can help them is to make sure that they have that foundation. So one of the things we're looking at is to take things like right now, we just show you where the latest data shows a satellite is. And there's a little timeline, a little scrubber that you can pull back and forth and go through. And what we want to do is switch, and we're working on doing that in version 2, is to be able to have it switch every time the data switches. So if you're watching, something going on where a satellite is maneuvering, say, to another orbit, instead of seeing the view at where it is now, you can go back and see how the orbit changed over time, or see, when somebody moves a satellite to, say, decommission it, or when they're doing maybe a collision avoidance maneuver. There's all sorts of opportunities there, and we're just trying to find ways to facilitate people learning and exploring and being able to innovate in this environment.
Well, then I'm extremely appreciative, TS, for us starting out where we did, right, with the 70s and the 80s and all those problems of standards and sharing information and collaborating and whatnot. And I'm not going to say it's super similar, but we're in a slightly similar situation today, but just with a way better starting point, it sounds like, where there are some standards, we can share this information, but then now it's up to you, listeners and viewers, to come up with, all right, what do we do with this? What's the next step? How can they collaborate with you, and how can they get involved and kind of stick up their hand and say, hey, I have an idea?
The easiest way to do it is go to CelesTrak, and every single web page has my email address. You click on it, it should launch your mail client, and then you can just send me your message. And honestly, I mean, obviously I have a lot of stuff going on, but I try to take about an hour a day at least just to answer people's questions. And you would be surprised where that comes from. I mean, sometimes it's from professionals, trying to work a particular problem, and in many cases, kind of helping me push what we should be doing on CelesTrak. It's like, yeah, we don't do that yet. Let me see if I can figure out how we can. To literally answering questions for high school kids in India, I mean, or anywhere else on the planet. Usually try not to do that within about a week or so I'm not doing their homework for them. but you never know whose spark you're going to help light that's going to go off and change the world. And so we want to do that. And I encourage any of your listeners that if they have questions and they can't find it already on CelesTrak, one, I want to know that, because if I get a lot of questions like that, I'm looking for ways to make that easier. But if you're doing something and you just can't figure it out, just shoot me an email and I'll be happy to get back to you. The other thing I would encourage is that if you're trying to stay up on current events and some of the highlights, like this morning, we finally got pieces. We got 22 of what looks like to be 25 pieces of debris for a NOAA 17 breakup event that occurred on March 10th. So, that went on CelesTrak, and I immediately put something out on Twitter, showing the orbits with the orbit visualization and making sure that they're aware of that if they happen to be interested. So you can kind of stay up on new launches and other things that might be of interest if you're, wanting to learn more about the community.
Fantastic. All right. And folks, be persistent. I know we we were laughing because it took us, and I really appreciate you coming back and booking this time. It took us months to arrange this. Very different time zones. Dr. Kelso's got work to do.
Imagine that.
But to his credit, we got this, and it's been a very good process to set this up. But if I had just given up after one attempt, we probably wouldn't be talking. Because other people, the squeaky wheel kind of gets the oil, would have been, higher up on the food chain. So, well, thank you very much for doing this again. It's been extremely informative. I've enjoyed it a lot, and getting to know you as a human being as well.
Okay, thanks. Really appreciate the time, and hope all your listeners enjoy it. Thanks, Jason.
Thanks for tuning in. If you're interested in working with us at CelesTrak, here are some of the things that we can help with. There's a lot of people who talk about process, documentation control, attention to detail, all this stuff. We help organizations become true learning organizations. Remember, if something isn't written down or recorded in some way that's accessible, searchable, findable, it didn't happen. It might as well not have happened. So if you have two people who solve a problem, a serious problem in your organization, but they do so in isolation and nobody finds out about it, which happens all the time, then it didn't really happen, and nobody else can access that wisdom. So we unlock wisdom for your organization. We do a lot of things in the space industry. We have access to regulatory and legal officials who can help you, if you're a space industry founder, find out what areas of regulation and compliance do you need to be working with, compliant with. And we find a lot of folks don't even know about some of these areas. They don't even know that they exist. Can you imagine how you're going to stumble and stub your toe and really screw up your organization's timetable if you don't know about these things? So come and talk to us. We've got great relationships with the right people, especially in the United States and in England, and we'll be able to help you with that. And so when it comes to process improvement, whether that's some sort of business documentation, business development roles, wow, have I seen some things in business development. You got founders out there who all they're doing is quoting on projects. This is a mistake. You are wasting your energy bidding on things that most of which you never even had a chance of winning in the first place. I've seen people bankrupt themselves bidding on everything, or bidding on only these high-end things and not realizing that you need to have a strategy so that this bidding process pays for itself. I mean, you got to learn how to screen here. And this is not something that they teach you in school. I had to learn it myself, so don't feel bad about it, but come talk to us about it, okay? So either it's on the business process side or the actual manufacturing of physical goods. That kind of process improvement. You can come talk to us. Can this be done faster, cheaper, better? And yes, most of the time it sure can, because people just do stuff, and the first person to invent the way of doing things is the person who gets to choose most of the time how things are done. This happens all over the place. I like to point out our traffic signals for automobiles are based on the way that they ran railway traffic 100 years before that, okay? So, and this is key in the space industry right now, which is new, right? This is an area that I personally am interested in. How we figure out how to do stuff today is going to impact generations, because people are so easily locked into this is how we've always done it. And if you hear that at your organization, there's a warning bell. This is how we've always done it. You need to come talk to us at that point, okay? So reach out to us. It's easy to do. Just message me on LinkedIn or email me at jason@coldstartech.com. I want to hear from you. Thanks for listening.